Now, when we talk about Ganges, we need to understand it is a transboundary perennial river. And as the river flows, it faces a lot of issues related to agricultural runoff, as the land is very fertile here. There are a lot of industries here, and dumping of domestic waste is definitely a serious issue along the riverine regions of several developing economies, and no way we are lagging behind in that. And there are a lot of activities, religious activities also takes place along this river. So waste is a big issue along the Ganges. I mean to say both solid and liquid waste. And in the recent years, we have seen that Indus, Brahmaputra and Ganga are among the top 10 rivers carrying the plastic waste across the globe. And Ganga is the second most polluted river in the world, spraying 115,000 tons of plastic each year. These are the kind of reports we are seeing. So, of course, it makes us evident to try to understand this project, the importance of this project. So, in my talk, I would be talking about like different kinds of additives which are added to plastics, and how do they end up in River Ganga. How did we plan the sampling design, what results we got, and we are moving towards a sustainable approach. I will be throwing some light on that as well. So looking into the scenario currently, like along the river belt in India, we see the huge quantity of plastic wastes being dumped. The littering of plastic is happening not only on the open dumps but also along the riverine region. And another important thing is, like, the moment the plastics are dumped, within some time, they are openly burned. And like any other developing economies, this is a very, very big issue. And this problem can be sometimes even more severe than industrial waste playing an important role. That's what actually I had been seeing in last more than 1 decade work that I'm doing extensively in India. And if it is rivers, they're source of fresh water many a times, and a lot of fishes are there, and the bioavailability of a lot of chemicals that are associated with this kind of dumped plastic waste are of significant concern. And that makes the problem statement, the plastic litter and the open burning of the plastic waste, which could lead to a lot of dangerous chemicals. Now, what kind of chemicals we may see is like, we can see a lot of plastic additives which are being added to plastic products, and to change the properties of the plastic, to give it durability or shape. And then there are some gadgets like electronic gadgets, etc., where flame retardants are being added. And many a times, many of these compounds are highly carcinogenic. Plastic monomers like bisphenol A, they are very, very difficult molecule to handle because they all cause endocrine disruption, like all this kind of chemicals that are added to the plastics or coming from the polymeric form or monomeric form can be very deleterious to human health. So what basically happens is that in the plastic materials, in the polymeric chain, be it polyvinyl chloride, be it polyethylene or polypropylene, a lot of additives, plasticizers, like phthalic acid esters, phthalates, they are being added, like and which makes the product maybe more flexible or to add softness to the plastic. And there are different kind of phthalic acid esters. Of course, 6 of them are enlisted as a priority phthalates because of their endocrine disruption potential and the toxic impacts that several of these phthalates do have. Of course, most of these phthalates, like which are having EDC issues, they are like about 5% of the total plasticizers that possibly we are using in the commercial products. If you look into the fact that in a global perspective, if you see that the packaging material is one of the important material, plastic packaging, where a lot of plastics are used, and then the electronic gadgets also has a lot of consumption of packaging material, not only casing, etc. And if we look into the plasticizers, the flame retardants, and these are forming nearly 40% of the total kind of additives that are being added to the plastic products. And plasticizers definitely, there are several such chemicals which are added and are of high concern, and some of them are definitely of higher concern. So if we see like what we are seeing past over a decade now, like that one is the open dumps, with the open dump sites where plastics or waste are being dumped and burnt. They are major sources of several such chemicals that come out of the plastic, because as I showed in my previous slide, that these chemicals are actually not chemically binded, they're embedded. So leaching out of some of these chemicals, especially these plasticizers that I'm talking about, that could be very important. And many places where, especially such as tourist places, etc., where the PET bottles, like till it was banned, etc., these PET bottles were being dumped, and a lot of quantum of waste they do come out. So that is kind of plastic related chemicals that also we are seeing. And it also leads to a lot of polycyclic aromatic hydrocarbons and many persistent organic pollutants as well. But in today's talk, I'm limiting it only to the plasticizers, which are actually, most of which are having endocrine disruption potential. Now, why this plastics, and how do we select that where to work out? Now, this was very important, like Lebreton et al., they came up with this paper in 2016. And if you see the dots here, which is the lower stretch of Ganges, we locally call it Hooghly River. This has a very larger dot, and if you see after Yang's River, Ganges tagged in the second place. It is a transboundary river in this area, it's between India and Bangladesh. And what we are seeing is the plastic loading, the waste loading flowing from the rivers to the open ocean are pretty high in this part, like over this Bay of Bengal, this area. So this was a similar time when we started working. We started working since 2015. Actually, we started working in Ganges and Brahmaputra since 2012. And 2015, we were focusing exactly in this area. And then we see these papers, which is also talking about the plastic loading in this area. So the objective of our project was to find out the fate of this selected plasticizers, their fluxes and the potential risk we can have out of them, and do we have some sustainable way to handle this issue. That's also what we are looking at. And monsoon plays an important role in India, and which is why it's also important to know whether the monsoonal variations are there. But of course, in this talk, we won't be talking much into the monsoonal variation part. I'll limit it to what we are seeing in the Ganges and the associated risk. So what did we do? We had a sampling design. The river covers nearly 2,500 kilometers. Our study area covered up to 1,700 kilometers with 14 stations. And we also had sampling sites in the Sundarban wetland, which is a pristine site, and the idea of taking it, because it's a World Heritage Site, it is also bordering between India and Bangladesh. So we wanted to see whether this pristine sites, the rivers in those pristine region, whether there is a variation. So in the entire river, Ganga River, has been divided into upper stretch, middle stretch, and the lower stretches. We have covered this 1,700 kilometers, covering to upper, middle, and lower stretches, and some of the estuarine points close to the Bay of Bengal. We have done extensive work, like for the fate processes. We have extensively worked in the lower stretch of Ganges towards the estuarine end, wherein we have looked into both riverine region up to the estuarine point along the Bay of Bengal. And we have seen that there are several these dark spots at the discharge points. And this also gave us a lot of information from the Central Pollution Control Board, like there are direct discharges in this region. To understand this better, we have used certain marker compounds for human waste like caffeine and carbamazepine. We have collected surface sediment, river water as our sampling matrices. And for Sundarban, we have also gone for air sampling, but I'm not including that in this talk today. So most of the sediment and water samples were extracted in normal procedure that most of us might be using. For sediment samples, we have used microwave assisted extraction, whereas water samples, we used SPE, solid phase extraction. And finally, with the cleanup procedure, we have subjected it for GCMS analysis. So apart from phthalic acid esters, we have also analyzed bisphenol A. And if you see here, that risk part, what we have worked out is one interesting thing for the entire stretch of Ganges. What we have done here, we have taken the sample extracts and diluted it in cell culture media containing charcoal, dextran, stripped fetal bovine serum, and analyzed using MCF7 BOS cells. And this cell line we exposed it to check the estrogenic potential of the concentrations that we had. I must say this, that since we were doing plasticizers and some of this plasticizers had estrogenic potential, that was the idea to do estrogenicity. At the same time, we have analyzed the steroids in those samples just to check, whether the estrogenic potential is could be due to the steroids also, or it is typically from the plastic additives. And apart from that, we use the PINEC values to the RQ, the measurements, and this risk quotient which we have done for sediment, surface sediment. From surface sediment, we have analyzed for pore water using TOC as an important factor for conversion, and we have also looked into the surface water, the ecotoxicological risk to different trophic levels. We have estimated the flux using the fugacity fraction, and we will see how different kind of phthalic acid esters or bisphenol A, like how they were behaving. Especially we did for those sites where we have seen both in surface sediment and surface water all the molecules. So those were limited to only those compounds which we are seeing in both the matrices. For GCMS analysis, I have to mention, since you might be surprised how am I able to do BPA in GCMS. Yeah, we are using a derivatizing agent, MSTFA, to derivatize and then analyze in GCMS. Now, to do plasticizers or plastic additives of this kind, we have to be very careful with the quality assurance and quality control. Apart from the LOD, LOQ or the normal surrogate recovery, we emphasize the fact that we use mostly glasswares. We try to reduce as much as possible to just use glasswares but not plastics. And every point we had several method blank, extraction blanks, and just to understand whether we are contaminating our samples during the process. Fortunately, our blank levels were very low, and even we have run air sampler while we were doing these experiments inside our lab. So these kind of quality control processes we were taking care. What did we see in our data? Now, firstly, when we went for the lower stretch of the Ganges, which we started with, in surface sediment, we were seeing there was high loading of plasticizers over several other cocktail of contaminants, which even included pharmaceuticals and preservatives and different other set of compounds such as antimicrobial agents, etc. So plasticizer loading was very high onto the sediment. surface sediment. Similarly, in surface water as well, mostly from the urban transects where we saw higher loading. And this is the urban transect caters to the freshwater region. But as we move to the mixed or the marine region, the levels were relatively lower, especially if you see that the levels when it comes to some of the pockets where there were tourist places, we could see slightly higher range of the plasticizers in those places. Stormwater in general had much higher level compared to the surface water, and which is expected because these are the open drains bringing in the city runoff and onto the river body. When we looked into the fluxes with the surface water and sediment, what we saw was that excluding DHP, most of this other phthalic acid ester and bisphenol A, of course, like they were more partitioning onto water, whereas DHP, the median value were was less than 1, and it was way lesser. So it was being a particle bound compound, we were seeing more onto sediment. So now what we did, we took the entire riverine stretch. You see we have placed the population map here in GIS mapping and placed the bars for the levels. Now I must tell here, I have introduced that we have used a marker compound like caffeine, which is a good well-established marker for human waste. And we see that middle stretch of Ganges, it has been well proven that it's highly polluted due to industries and a lot of direct discharge points, and which was coinciding with a lot of discharge points. But now what did we do? Apart from this marker, when we were analyzing the plasticizer, we have subjected the concentration of the water that we collected from each site for the cell line study. And during this design, what we tried to see is that E-screen E2 equivalent value for certain sites where caffeine was also high, we found that this E2 equivalent were much higher, which means the estrogenic potential for those sites were way higher. Interestingly, those sites we didn't see steroids at all. See, the star points are the ones where androgens were only detected. So we were not seeing steroids at all, but we saw the estrogenic potential. So we have come to a concluding remark that this is because of the plastic additives that we are seeing. And the concentration, if you see the plastic additives concentration are among the highest, this M11, are among the highest of those that particular area. If I take average out also this area, they are the highest levels of plasticizer that we saw here was this one. So if we are seeing this estrogenic potential in a human cell line, it is having a direct impact. And as I mentioned you, this is a freshwater resource. So the possibility of impacting even human health in the long run would be there. There is an exposure pathway. And even some sites in Sundarban wetland where actually there was this aquaculture pond, and we are expecting because of the fishing nets, etc., the plasticizers level shooted up. And this was the dominance we saw was mostly because of diethyl hexyl phthalate, which is a proven endocrine disruptor. So this elevated levels of plastic additives are not only there in these industrial areas, but also tourist spots. So this wetland area where we saw higher concentration, even where we saw high levels of not only phthalic acid esters, but also bisphenol A, was also a tourist spot along the lower stretch of the Ganges. So this we are suspecting that because a lot of single-use plastics during that time, it was not banned, and PET bottles, that could be a source, a pathway for these molecules to enter into the surface riverine region, surface water, especially contaminating the surface water. The associated risk, if we look into the fact, what are the risk we are seeing? Of course, we have used the Cespedes et al., the yeast assay, that also we have used, and we saw that stormwater posing the most risk to the estrogenic potential compared to other water regions like freshwater or marine regions. And of course, because the levels were also higher, so estrogenic potential based on the yeast assay, what we used were high. And one interesting thing is on the sediment, there will be this pore water. When we saw the risk in the pore water were way higher than surface water, which is obvious because the concentration in the pore water would be very high. So that is pretty much well accepted. And we can predict that this could be on a higher risk, especially for those flora or fauna onto the sediment. They might have a higher impact. This gives us, as I was mentioning, the tourist spots. Why we were thinking like this, like we did a leaching experiment in our lab and we found that these plasticizers are getting leached, especially from those brands which are using recycled polymeric material, recycled plastic. And from there, many of these compounds which are coming out that can actually contaminate the surrounding environment, which is a possibility. So this, we did an in-house experiment, and I must tell you, like many parts of India where in summertime, many of these bottles are kept outside the shops, and then again they are sold out. So we have done an experiment where we have increased the temperature and seen that even like in a normal 25 degrees centigrade, it's a normal room temperature for 48 hours, this recycled brand was giving out more plastic additives when compared to the other pristine or the virgin pet bottles. So that was one important thing that we are coming up, that these chemicals would be coming out from this recycled polymeric material. So we should try to minimize use of recycling polymer for food packaging or beverage packaging. We have some sort of future plans. This is just the beginning of the research, and as the pandemic hit, we are seeing like the quantum of plastic waste onto the solid waste stream has tremendously increased, especially associated with PPE kits, etc. And of course, South Asia will have a genuinely big problem because already we are struggling with the waste related problems. So what we have already started seeing is, like due to the open burning, we are seeing some of these chemicals which could be associated with open burning are much higher, has increased like in some cases over 200 folds after the COVID-19 pandemic. And we are also looking into the bioavailability of many of these chemicals that could come out or leach out from plastics. So to summarize the talk, I must say that we are working into the plastics chemicals interlinkages. Plastic additives are something that I just introduced the problem. We are also looking into the flame retardants or several byproducts. And there are different solid waste stream that is coming out where the plastic can be associated with different sort of chemicals. We are trying to look into that in our ongoing projects. And as I started with the problem statement, we could see that most of this leaching, most of the chemicals that are coming out from the plastic litter, especially it is aggravated when there is open burning. We are working on a solution which is like a nanoparticle augmented constructed wetlands, trying to see that if we can help the riverine system to have a better way of handling this wastewater out of plastic additives. We have named this as a mantra pot, and the idea is like we will have a nanoparticle layer below the constructed wetland and can get water which may not be potable but can be used by industries or by for the other local activities, say for example washing, cleaning, or even to some extent it can be used for different other household purposes, not but associated with cooking or drinking purposes, of course, not for that, not potable ones. We have also worked out like we are working in the patenting this product and using it in a larger scale, trying to support in our, we have a Swachh Bharat adopted villages, we are trying to bring it up in those villages now. very soon we will be deploying such chambers there. And since macro and mesoplastics are important, it's also important to do microplastics. So we are not limiting only to do microplastics, but we are also looking into this kind of plastic additives in different forms that are there in the microplastics. We have just started this work with the microplastics, and we have our own medical school, so we are also looking into the fact that how this chemicals could enter the food chain and also impact human health. So we are looking into the placental transport ending up in the human milk. This is what we are looking at. The project that I was mentioning has been supported by Indo-US Science and Technology Forum, so I have to acknowledge, and Department of Science and Technology, Government of India. Some of the slides I mentioned also was funded by Ministry of Environment, Forest and Climate Change. And our future work is a part of India-Norway Marine Pollution Initiative, India-Norway Cooperation Project on Capacity Building for Reducing Plastic and Chemical Pollution in India, INOBOL. We have partners, Norway Institute of Water Research, THERI, Myogama, CIPET, Toxics Link, and I'm leading from SRM. So these are the future work that we are aiming to do in this project. And last but not the least, my entire group members, this Environmental Science and Technology group members. I am very thankful to all my students, my collaborators, my scholars, research scholars, who helps us and enables us to bring in such important data for the government and for the policymakers as well. So, and thank you very much for your attention. And I thank Professor Daniel Snow, who was a very big collaborator for this important project, and I was working on Worry Fellowship in US with him. So this credit also partially of this talk goes to him as well for being such a wonderful collaborator. Thank you. Thank you very much.